In this supplemental video, we're going to cover where the area for the shapes associated with Simpson's rule come from. So remember Simpson's rule, the idea was we're trying to fit a shape with a parabolic cap under the curve in each partition. So we're going to discuss where this area formula actually comes from. So the area formula for Simpson's rule was that the area equals the delta x over 3 times the left point times 4 times the middle point times 1 times the rightmost point function value. So if we're thinking about this, without loss of generality, we're going to think about maybe Simpson's rule, but on an interval between minus h and h. So the midpoint for us will be a 0. This is, of course, on x and y. So if we have some function, what we're really going to ask here is, how can we fit a parabola between 3 points? So this parabola will have some shape, and what we're going to do in this video is basically talk about the derivation of where the shape area comes from for something like this. So we're going to derive this equation in the middle here. And the first thing we're going to really consider is that this parabola, we could write as a general parabola with coefficients a, b, and c. So ax squared plus bx plus c. And we actually won't really concern ourselves with where these coefficients are coming from in this case. But this is going to be the parabola that we play with going forward. And this is a parabola, again, that is fit or that touches these 3 points. And these 3 points are going to be the ones that we use in Simpson's rule. So just to reorient ourselves a bit here, what we're really saying for this Simpson's rule type of shape area is the distance between minus h and 0. This is our delta x. And the distance between 0 and h, this is our delta x. So to put ourselves sort of in the language here for where the Simpson's rule formula comes from, these are our intervals between points. So delta x, in this case, delta x is equal to the absolute value of h, in other words. So the first thing we're actually going to do here is just define a few of these points. So we could think about this as sort of our left point, and this would be the function value associated with that left point. We would have the middle point, xm, and this would be the function value associated with xm. And then the rightmost point would be xr, and then the function value associated with xr. And of course, in this case, we know that xl we're thinking about as minus h, xm we're thinking about 0, and xr we're thinking about positive h, but this generalizes even more. So all this to say, what I want us to focus on first is we have a parabola that touches these 3 points. Let's compute the area of that parabola. Or sorry, the area under the curve of that parabola. So part 1. If we're finding the area under the curve of that parabola, well, that's the definite integral between minus h and h here, the leftmost point to the rightmost point. And then we get to stick in our parabola formula, the ax squared plus bx plus c. And that's with respect to x. And remember, a, b, and c here are some known numbers that will just give us the parabola that touches those 3 points. We actually won't really care what those values explicitly are in this case. So now we have a definite integral to compute, and this is a nice parabola. We can compute its definite integral. So integrating, what we'll get is a over 3 x cubed plus b over 2 x squared plus a c times x. And again, we're going to evaluate this at minus h and h. So the next step, once we have that antiderivative, plug in the bounds, upper minus lower. So we'll have a over 3 times h cubed plus b over 2 times h squared plus c times h. And of course, that's only the upper bound. But next we get to evaluate the antiderivative at the lower bound as well. And we'll see that it looks very similar, but wherever we had an h, this is minus h now. So let's plug all that information in. Right, and we're going to see that a lot of cancellation actually takes place here. Namely, the term that we're going to see gets canceled is this middle term, the b over 2h squared, and the b over 2 positive h squared that comes from that minus h squared being squared. Those two will cancel because of that subtraction in the middle. But everywhere else we'll essentially get 2 times those values. So we'll get 2 times a over 3 times h cubed, and then we'll get a plus 2c times h. So that's what we have so far from this area under that general parabola that we have. Again, parabola with coefficients a, b, and c between minus h and h that touches those 3 points that we wanted at minus h, 0, and positive h. So the next move we're going to make, and this is just going to be because it helps us out later, is we're going to pull out a factor of h over 3 from both of these terms. So if we pull out an h over 3 from that first term, we will get a 2a h squared. And if we pull out an h over 3 from that third term, well, what we're going to get then is plus 6 times c. Because again, we're trying to pull out a 3 from that denominator. So we had to multiply both the top and the bottom by 3 over 3. All right, so that's it for part 1. This is the area under that general parabola we had that touches those 3 points at minus h, 0, and h. And again, to remind ourselves, the way we're thinking about h in this problem is h is really our delta x. And the only reason I'm pointing this out is if we compare that formula for the area for that function, for that particular shape, we're starting to see that sort of delta x over 3 beginning to show up. Right. Well, that's part 1. We integrated that general parabola. Part 2, if we have a function for that parabola, f of x equals ax squared plus bx plus c, and we know the x values at x equals minus h, x equals 0, x equals h, we can plug those values into this general parabola. So next, let's go ahead and do that. So we're plugging in the value at, let's say h. So if you plug h into this parabola, we'll get a times h squared plus bh plus c. We can do the same thing and plug in that middle point now when x equals 0. And if we plug in 0 into that parabola, well, this is really nice. The x squared terms cancel, the bx is 0, and we just get f of 0c. So finally, let's plug in minus h into this. So plugging in minus h into this parabola, we will get a times minus h squared, which will just result in an h squared for us. Next, we'll get b times minus h, and that'll result in a minus b times h this time. And then we get a plus c. So why is this important? What did this actually buy us? Well, in a moment, we're going to add together these things, except we're going to try and add them together in a clever way to try and give us what we see above here. So let's go ahead and try to do that. And the way in which we'll add these together, it turns out, is what we're looking for. If we look back at basically this term in the square brackets, we will have no BH terms, no B terms anywhere. Well, what that looks like is if we just add this equation and the bottom equation together, f of h and f of h are at minus h, the BH terms will cancel out because of the change in sign. And then the other thing we need to figure out is, well, we'll get a 2h squared if we add together f of h and f of minus h. So we'll get the 2ah squared that we see up there. The only thing left, though, is we will only get 2c at the end. But up here, we have this 6c. So the way in which we can compensate for that is basically by adding 4 times this middle equation to it. So let's just go through these steps more explicitly. So if we have f of positive h, and we add together 4 times f of 0 plus 1 of f at minus h, what we're going to get is the following. So we have ah squared plus bh plus c. We will get plus 4, and f of 0 is just equal to c. And then we'll get plus 1 times f at minus h, which is ah squared, minus bh plus c. So if we add together all of these pieces now, what we'll see is the plus bh and the minus bh cancel out. We'll next get this ah squared plus ah squared that results in a 2ah squared for us. And the last thing we'll see is we have a plus 4c, a plus c, and a plus c. So this results in a plus 6 times c. So why is this important? Well, if we compare back to what we did for the integration, we now have this combination of function values that lead us to something that looks like 2ah squared plus 6c. And that is awfully reminiscent of what we got from that area integration from before. But the only thing missing is that coefficient of h over 3. So this brings us to part 3, where we're going to synthesize a lot of this information. In other words, by adding together these function values, like we did here, we can get something that looks very close to the area under that parabola exactly. Except we are missing that coefficient out in front of h over 3. So part 3. Basically, to make the summation of function values and the area under the parabola equal, so to make area under parabola equal sum of function values, what we need to consider then is, again, we have h over 3 times 2ah squared plus 6c. So what we're going to do is just take that summation of function values, and on top of that, multiply it by h over 3. So we need h over 3, and then times that special sum of function values, f at h, plus 4 times f of 0, plus f at minus h. And this is actually really reminiscent of this area formula that's highlighted on the left-hand side for the area under one of those parabolically capped regions. The only thing that's different is, remember, our h was actually equal to delta x. The way in which we defined these points previously was, well, x equals 0. This was our x middle point. And I guess I swapped the order of the sum here a bit, but f at h, this was our rightmost point, xr, and f at minus h, this was our left-hand point, xl. So in other words, by using these 3 points, the left, middle, and the right, we were able to come up with an area for one of those parabolically capped regions. So the area formula we have is really delta x over 3 times the sum, and I'm going to swap the order here, f on the function value at the left side of this, plus 4 times the function value in the middle, plus the function value on the rightmost side. And that is where the area formula comes from for each of those parabolically capped regions that we use with Simpson's rule.